Right, let's go through this. Are you ready? Now, are there any disagreements? Any questions? Because we're just looking at the carbon at this as the central atom. So around the carbon, you'll have 1, 2, 3, 4 things. The OH, you almost, yeah, you almost treat that one. Yeah, then you can't. Then it's going to be complicated. Yeah.
Most at the bottom of octahedral country.
Because you remember octahedral was this one, yeah. This one. Sorry, this one here. So you got 180 there, but actually we look at the bond between each thing. So this is all the bonds are actually 90. Yeah. Guys, there's a very nice piece of software that you might want to think about. Well, let's just go back here first. Any other issues with any of these? Which one? PCl5. So that's the one with 5 things bonded to the central atom. And I showed you the shape yesterday. They just go naturally into trigonal in the middle and 2 sticking out. So that's this shape here. That's this one here. 120 in the plane, and then these 2 are basically 180. So you say it's 90 between there and there.
So is 120 and 180 right?
You can take a picture, yeah.
It's is 120 80 correct? Just
I wouldn't say 180 because 180 is going straight through the thing, but you'd actually look at the bond between 2 adjacent things, and it's 90. So this bond here is 90. So let me just show you this piece of software, which I think is really useful. Yes, go. Thomas? No. No. You need to know those ones that are filled in for you. There's 1 or 2 others, so you'll learn as we go along that. So, for example, this one here, D, which I didn't show you, is actually ammonia. That's a distorted tetrahedron. It's F, but one of them is a lone pair. See. And then, so some of these other shapes we never see. I mean, I don't know any molecule that's like G or E or H.
So H also have a lone pair.
Yeah. So H, what is H? H is basically one of these, where this thing here is a lone pair. See. So the only ones we deal with are the ones I gave you.
Four bonded pairs, but it's a sequel.
No, 4 bonded pairs around the carbon. That's what I'm trying to say. 4 bonded pairs around the carbon. Specify that. Say that again. For PCl3, isn't it? We'll stick to what the notes say. It depends how accurate you're going to be. I think 107 is accepted, but I actually think it's 107.5. But we'll check on the notes. So, guys, when it comes to studying for your exams, I use the PowerPoints to teach because it helps me explain each concept. But when it comes to studying from exams, study from the notes. Okay? That's where we set our exams from. So then the notes, everything we do in the PowerPoint is all in the notes. It's set out there a little bit easier to study from. You study from the notes. And then these little small things you won't have a problem with because you work from the values in the notes. Thomas.
So go back to slide 2. I think.
Okay, what I will do at the end of the PowerPoint is I will put the PowerPoint up, the completed one up in Teams. So you can get anything there you must. But if you want to take a photo, go for it.
That's
Sorry?
slide 2.
Slide 2, which is slide 2? This one. Okay. That's CCl4. Right. So some of the textbooks, I mean, I'm saying it's 109.5. I think that's more accurate. Some of the textbooks say 109. You know, that's neither here nor there. All right. That is your table. I just finished off this PowerPoint with a couple of examples in a bit more detail. PCL 5 is a good example of this trigonal bipyramidal. So there's the Lewis diagram, right? 5 bond pairs. Now, how do they bond? They bond like this. So you can see these two. Now, I know here I've said Cls, and in this diagram I've got fluorines. Well, fluorine and fluorine are above each other in the periodic table. It forms exactly the same molecule with both of them. So, you know, I just got, but I don't know why I did that. I've only just spotted it now. But anyway, so they would be exactly the same. I'm just trying to explain the shape a little bit more here. These two are obviously 180 degrees away from each other, but in a plane below them, there's 3 that are at 120. So I'm trying to illustrate that plane here as a triangle. Now, where does the shape trigonal bipyramidal come from? If you take the point of each of these external things and link them up, you can see here you get a solid shape. And that solid shape would have 3 sides on the top and 3 sides on the bottom. So that's a total of 6 faces. Now, it's not significant in this molecule, but it is in the next one. So this is a trigonal pyramid at the top and a trigonal pyramid at the bottom. And that's why it's called trigonal bipyramidal. Hopefully that all makes sense. I don't think you can show it much clearer than that. Defy anybody to come up with a slide that shows it better. Yes. Sorry, was that a question? Matthew? Was that a question? Oh, okay.
So
Yeah.
how would you draw PCL5 an example, the shape?
We very seldom ask you to draw it. We ask you to just name the shape. We normally, if we're going to ask this, we ask you the Lewis diagram, or we ask you how many lone pairs or bond pairs are there around here, or we ask you to name the shape or give us the bond angles. We very seldom ask you to draw it because drawing it's a bit of a nightmare. And then this one is SF6, sulfur hexafluoride. I've done the same thing here just to show you why we call this thing octahedron, octahedral structure. Where does oct come from? Oct is how many? 8, but there's only 6. So what are we talking about? Well, if you look here, there's the Lewis diagram. There's your 6 bond pairs, no lone pairs. Sulfur in the middle with 6 atoms around it. How are they arranged? Well, there's 90 degrees between all of them. And you can see there's a square in the middle, sort of a flat plane, where the previous one had a flat plane of 3. This one has now got a flat plane of 6. Sorry. Yeah. Sorry, a flat plane of 4 in a square, and then 90 degrees going through it. So if you linked up all the external atoms with these dotted lines, what have you got? You've got a square-based pyramid on top, and you've got a square. I don't know if you can see this thing in 3 dimensions. You can see that in 3 dimensions. Yo, I should have shaded them a bit better. It's a square pyramid on top and a square pyramid on the bottom. And the square pyramid on top has got 4 sides, 1, 2, 3, and 4 on the other side. And the bottom has also got 4. So you get 5, 6, 7, and 8. That's where the 8 comes from. It's an octahedral structure, octahedral shape. It's got 8 faces. I hope that makes sense. Right, it's break time. Go and have a break.